So I haven't posted a new homework, being that there is an exam right now we have, so. I'll encourage you guys to do more problems on Hamiltonian. So I think best way to encourage you guys is to say that I'll ask the question of Hamiltonian in the exam. So homework 4 is over, no homework remaining at this point. So we have midterm 1. Yes, close with that. Yeah. So as I said, I felt that I did not cover sufficiently or sufficient examples to show that how to write the Hamiltonian equations of motions. So I'll do few examples that elaborates on that. It's some of it is in your homework, but I will nevertheless go through it because almost half of you at least showed concern that how exactly to get Hamiltonian equations of motions. I'll go through that. There will be a problem on, or I intend to put a problem on Hamilton's equations of motions. So that gives you a rough idea, but at this point, I've given you so many questions that it is possible that it's not clear which one I'll put. Okay, so let's do example. Right, so as an example, we have now introduced a Lagrangian and a Hamiltonian. So let's think of a simple problem, harmonic oscillator, right? So harmonic oscillator. So this is harmonic oscillator. And this is there in your homework too. So typically what we do is that there is a mass m, and if this was x equal to 0, that's your x, it experiences a force kx to the left, right? If you stretch it to the right, it gets pulled to the left. Our equations of motion is Newton's laws, so it is m second derivative of x dt squared, that's equal to minus kx, right? There's only one variable, so you have only one. We don't have to use vectors. Okay. Write this equation in the form d by dt of mass times velocity, right? And that's equal to minus kx. And here v is a short form. If you want for dx by dt, x is the free variable. Compare this with your with the Euler-Lagrange equation. So we have d by dt of dl dp is equal by dx. So that's our Euler-Lagrange equation that immediately lets us, a possibility is that this is MV. This is not really a proof. Remember that Lagrangian is not unique, so this only gives you a hint of how to proceed from this point on to build Lagrangian. The final proof is always that once you have the Lagrangian, you should be able to do the variation principle and get this. Right, so you have to do the reverse process afterwards. So second or the derivative of the Lagrangian with velocity is mv, and we also have the L by dx is equal to minus k. Immediately you say that this is equal to, a possibility is that L is equal to half mv squared. That's it. When I take a derivative of this, it surely gives me mv, and this one seems to suggest that L is equal to maybe half kx squared. So that's the two possible solutions, but then you realize that this one has a constant, let's say f1, which could be anything independent of v. That means it can be dependent on x, and in principle t also. And here you say that this could be dependent on v and could be a function of t also. As I said, Lagrangian is not unique, and maybe like you could propose that Lagrangian is half mv squared minus half kx squared. Right, but that's a proposition. You have to check from this point on that if you do the variation, you will get back your equation. So once you have the yes.
Do we have to always show this F1 and F2 in the?
No, you don't have to. As far as you guess this, that is okay.
Oh.
And this gives you a hint as to how to look for. Once you have seen 2-3 examples, it turns out that it always works out well. Challenge is, as I suggested, that do this for the drag problem, and you will see that there are challenges. Like this seems very simple because once I give you, then it is simple. That's where I suggested that do this for the drag problem, and it doesn't come out straightforward. Any drag, put the linear drag, let's say. Like that's what I was suggesting, that maybe that would be an exam problem. So construct the Lagrangian out of it, and you will see that there are challenges. So anyway. So what I was saying is that, yeah, as far as you can build a Lagrangian that gives you the equations of motion, that's good. This is a small hint as to how you could proceed. This is surely not a full proof because F1 and F2 is not unique, and you have two solutions, but nevertheless a guideline for you. How you could, is that the answer? Okay. Once you have the Lagrangian, you write the action, right? Action here is only dependent on x, equal to t1 to t2 dt, and the Lagrangian, which is half mv squared minus half kx squared. And maybe it helps to write this is dx by dt squared, right? That's velocity, but it's understood. And do the variation of this stage, which is pretty much what will give you this variation of x with respect to x, let's say at t prime, right? That's equal to, you will have there will be a d by dt of this, so it is minus of d by dt mass times, let me write that as velocity, right? And jumping few steps here, and minus of kx. Right, yeah, which is of course here, so now that's not yet, I have not used the stationary action principle. And this will be a stationary action principle, let's say. Implies that d by dt and v is equal to minus k. So this is a check that, okay, this Lagrangian really gives you the equation of motion. Go back to the Lagrangian again. So Lagrangian is equal to half mv squared, maybe say Lagrangian is a function of x, actually, x of t, and x of t, dx dt, and that's the quantities it depends on, and that's equal to half kx squared. The moment you have a Lagrangian, you can take you can define what is called a canonical momentum. Is P, and that's dL by dV, where V is dx by dt. So pretend that x and derivative of x are independent variables. We have been doing that whenever we did the functional derivative. We pretend we take derivatives with that. That's the canonical momentum. In this scenario, in this simple example, this is the usual linear momentum that we have. That's just a coincidence. It need not be the case. Magnetic field, you saw that this is not always MV. So there will be situations where this is not MV, so be prepared for that. But once you have the momentum, then you can define the Hamiltonian. So once you have the momentum, you define the Hamiltonian, which always is by construction. It is not that you force it to be a momentum property. It will not depend on velocity. This in the way the way I define this will be V times P minus Lagrangian. Like Lagrangian depends on velocity, position, and time. There is a momentum that I have defined. So you would expect that this should have X, V, and P, right, and time. But always this will not be there. It will go away. Like whatever is in the Lagrangian, this will cancel this out. That is the way this is constructed. Any problem, this will always work out. That's the idea of canonical momentum, that the moment you bring in canonical momentum, the velocity goes away. And because it goes away, you should never write it as a function of velocity. You should always write it as a function of momentum. So even though it might seem that it is possible to, right? So Hamiltonian in our case, so this is equal. So x p if you want, that's equal to V times P minus of the Lagrangian, which is half mv square plus half k square. This is surely a Hamiltonian, but it is not in the true sense because we have written it in the form of V. So I have to get rid of my V in terms of P. So V is equal to P over M. Always the canonical momentum will give me a connection between the velocity and the momentum. Use that to get rid of the velocity here. Right, so this will be equal to V is P square over M minus 1 again 1 by 2 M P square over M square plus half kx square. And this is what P, so This is p squared over two m plus half kx squared. Which connects with our idea that Hamiltonian is the sum of kinetic energy plus potential energy. This is kinetic energy, potential energy. The only difference is that this is written in the terms of momentum p. That's important. Okay. And it will have only xp, and in this case, it doesn't have any time dependence. It could have a time dependence if you want to. It is Hamiltonian is usually associated with energy. If it is time dependent, it is not a conserved system. If it is time independent, it is exactly the energy. So, so that's your Hamiltonian. Once you have the Hamiltonian, you can have the action again, right? So you have the action again. And let me keep this open. And now T1 to T2 dt, that was your action. But I can replace the L in terms of the Hamiltonian. That's T1 to T2 dt. And now you have Lagrangian is V times P minus the Hamiltonian. This is now X and P dependent. And P also. Because as I said, V will be not there, so you have X and P dependencies. So there will be two variables here, and now you can vary both in terms of X and P. We will do the variation, and the variation with respect to X comes out to be, this will be dP by dt X. So x by dt. So these are called Hamiltonian equations of motion. The x by dt will always be equal to the Hamiltonian partial derivative of the Hamiltonian with respect to p. We'll do that in a minute. And when you vary it with p, momentum, this gives you the total time derivative of the momentum with respect to time is equal to minus of the partial derivative of the Hamiltonian with respect to x. Let's see what this implies. We have our Hamiltonian. Hamiltonian is, excuse me. Yes. Okay. Good. Let's 3. Thank you. Yeah. Okay. Thank you. Yeah. Do interrupt me. Okay. Yeah. Even though it seems like you're in a flow, so interrupt me. That's, I think, helps. Okay. Hamiltonian was p square over 2m plus half kx square. Notice x and p, only x and p there. If there is a v there, you will miss some derivatives. That's the whole point. When you take the partial derivative with p, if you were to write this in terms of v, then you won't see the p there. It is important that before you do this equation of motion, you have to write it in terms of x and p. Only x and p, v should not be there. We will not be there in principle if you were to take care of it properly. Derivative of the Hamiltonian with respect to p is equal to, there are two of them, so that's p over m, and derivative of the Hamiltonian with respect to x is equal to k times x, right? So the two equations of motion in this particular problem is dx by dt is equal to p over m. This is consistent with our understanding that momentum is mass times velocity, right? So you don't get anything new because we are doing the same problem. We are writing it in 3 different ways. And the second equation is dp by dt is equal to negative of that minus kx. And if you combine them together, you do get your original equation back, right? So this is Newton's law. This is Lagrangian, Euler-Lagrange equation, right? This was Euler-Lagrange equation. is the Hamilton equations. All three are the same, but different ways of approaching. Right? One tells that Lagrangian is minimized, the other tells that, or the one tells action in terms of the Lagrangian is minimized. The other says that the action in terms of Hamiltonian is minimized. And the third is Newton's law, which simply tells us the equation. All three the same description. Physics doesn't change, but our how we get the equations has changed. We think of it as an action being minimized. Okay, clear? Okay, so that's a simple example where you see the construction of Lagrangian. First comes Newton's laws, typically, because we work in Newton's law. Think of Maxwell's equation, for example. That's one of the hardest. Think of Maxwell's equation, build a Lagrangian for it. Right? Not extremely hard. We can do this in this course. It's very easy at this point because we have had them. It's just it has more variables. We have an electric field, we have a magnetic field, but otherwise it's pretty much the same idea. Your Maxwell's equation, we'll write the Lagrangian for it. Once you have the Lagrangian, right, find the canonical momentum for it. Once you have the canonical momentum, build the Hamiltonian, and then you will have Hamiltonian equations of motion. And quantum mechanics can be done in two different ways. One is usually done in Schrodinger equation. That's typically the Lagrangian sets of equations. And another way is the Hamiltonian equations. And Hamiltonian, since it is very fundamental in quantum mechanics, it is convenient to work in with Hamiltonian equations of motions, which in quantum mechanics takes the form of Heisenberg equations of motion, because there we write it in terms of commutators. We will see that here. We will see the shift from classical mechanics to quantum mechanics. We will do work in terms of Poisson bracket. And once you change Poisson bracket to commutator brackets, that becomes quantum mechanics. So we will see that connection here. It's very nice connection, but it doesn't help you too much with interpreting quantum mechanics, but it's a nice interpretation. Okay, any questions? Okay, so in your exam, what I expect is that I'll give you some problem like this, and you have to probably get the Hamiltonian equations of motion or Hamiltonian itself, something like that. So let's do another example which has a vectorial nature in it. Comments? Yes. Any comments? No. Okay. Yes, you have. No.
No,
No. Yes, okay. Yeah. Yes. Stop thinking, it's good. Okay. One of the popular problems, historically speaking, is the Kepler problem. And our Kepler problem was very successful in explaining or predicting the motion of planets. You could look at the telescope and say that at this particular minute, you will have this particular planet crossing some point in the sky, and it was extremely successful, and that's the whole idea of Kepler's laws of motion. So we should be able to get that using our simple equations, or Newton's laws. What are Newton's laws for Kepler's Kepler problem?
Newton's law of gravitation.
Yeah, and help me. So this is, let's say you have
Areas.
sun, let's say M1, and that is M2. That's a planet. It apparently goes on along an ellipse. Let's have the situation where M1 is very large. Right. Uh, what is the relative mass of Earth and Sun? How Sun is how much heavier than
Is,
10 times, 5 times?
it's like a little. The size of the earth is like a sunspot. Relative to the actual
That's
sun.
correct, but that's the visual scale you're saying. But if I were to tell it in mass, is it 10 times? Is it a billion times? Is it a trillion times? Is it 100 times? It's a million times. Okay, it's 10 raised to 6. Okay, so the basic idea is that if we don't account for, if we pretend that sun is stationary, we don't lose too much information. It's only in the fourth or fifth significant digit, all the corrections will come in. Jupiter, similarly, you would say that when you're taking care of Earth's motion, there should be all other planets' motion that shouldn't be taken care of, right? Is that important? How important is it? For example, Jupiter is significantly heavy. How heavy is Jupiter? Sun is a million times heavier than Earth. Jupiter is half of Sun? No. So it's about 1,000 times, right? So 1,000 times heavier than Earth. Sun is a million times heavier than Earth. But so the question you can ask is that when you're talking about Earth's motion around the sun, is it important to take care of Jupiter? Like if I do not take care of Jupiter, and that's important because three body problems are very hard.
And you'll miss the model.
Yeah, so the question is how much do you lose information? And it turns out again, if you're in two significant digits, okay, then you don't have to worry about Jupiter at all. Even if, for example, most of the predictions that you take care of, you can ignore the first order corrections you can ignore, but then they did get very good at it. They did take care of one planet affecting the other, and it did play an important role if you're aware of it. Like there are how many planets, by the way? 8, right?
9, 8.
Eight, right?
This
Yeah, let's not worry about the Pluto. Like Pluto is was a planet probably in your lifetime when you were born. It was that. Then it was removed. But without Pluto, there are 8 planets. How many of them are visible? If you go out in the sky and look for it.
To Saturn.
Up to Saturn, right?
Here
You
is
cannot
Neptune.
see the Uranus and Neptune. So 8 minus 2 is 6. And we are sitting on a planet, so we don't see it in the sky. So that leaves 5, right? 5, and then there is a sun and there is a moon. So that makes it 7. And those are the names of the days in a week, right? So 7 days in a week, always in almost every culture, they are related to the 7 objects that are going around in the sky. And there is a pattern in all these things. Whenever you look at the sky, if you look at it carefully, there is a pattern in this.
You can predict like when Jupiter will come.
Correct.
August clouds.
So 7 planets you can see using your naked eye. 2 remaining, Uranus and Neptune, was seen only after the telescope came in. Okay. And now the point is that both these planets were predicted. Like it is not that, see, for example, if you have you ever seen through a telescope?
Yep.
Have you ever focused, set a telescope up?
Yeah.
Right.
Saturn.
If you have set it up, you will realize that it is very hard to look at a planet because it's a big empty space and a planet is really tiny in a telescope's field. And when you want to search for it, it is really hard to search for it. So if you don't know where to look for it, it is almost impossible to find it. So even if there is a planet, just by having a telescope, it doesn't help. You cannot find Neptune or Uranus unless you know that where to look for. Right? Otherwise, you will just think that there is something there and you will never know what it is. So
Actually
both,
ran into that problem Sunday night, setting it up.
oh, so you are going to be doing
That we-
so then you know, okay. So I'll encourage you guys to set up a telescope. It is good to know that how hard it is. It is not easy. It is almost like saying that there is some scratch on this table and look for the scratch. Like just by looking at it, it's possible to see. So you need to focus it at the right or set it up or direct it in the right is the sky. Yeah. So in that spirit, Uranus and Neptune was not just accidentally found, it was looked at. So they noticed that there is a difference in where Saturn is coming in. Every other time there was a disturbance in the orbit of Saturn. So the prediction was made that there must be another planet disturbing it. And they gave the position of the planet at certain time and they looked for it and immediately within few days they found it. So that's very remarkable if you notice in the sky when you have 5 planets already existing and 5 plus 2 like Sun and Earth, and suddenly you say that no, if you look at it there is one more planet and you really look at it and it really exists. That was a huge success, right? That was appreciated too much. And then came Neptune and Uranus. Both of them were predicted in that way. It was predicted and they found it. And similarly, that is all the stories where then they started predicting too much, where there is a planet called Vulcan. Like, are you aware of Vulcan?
Yeah, I also where there's would be a possible planet 9.
Yeah.
All
So
the moons around Neptune, habitable objects into it.
look up Vulcan quiz. Right, quiz Vulcan, right? The idea is that similarly, when there were perihelion of Mercury was not being explained, they assumed that there is a planet very close to the sun. Earlier, planets were always outside, like the heavier planets are always inside. Then the assumption was that put a planet very close to the sun, and that will explain the orbit of Mercury. But let me not go in there. So my point was that Kepler problem was very successful, and we will assume that M1 is very large, very large, which is fine with Sun, in the case of Sun. So M1 doesn't come into picture at all. And then what is the equation of motion for the mass M2 then? What is Newton's laws for mass M2? Yeah, so what's the Newton's laws, like left and right?
What was it again?
Like what's the equation describing the motion of M2? Oh, that's Kepler's laws you're saying. No, Newton's laws I was asking. Just Newton's law. Right? No? I think you're misinterpreting my question. I'm asking just Newton's law for M2.
Isn't it the period squared is equal to?
That's Kepler's law. That's Kepler's third law. Right? That's what Dilakshi is also saying. I'm just asking Newton's law. Yeah, force is equal to?
MV is God over.
That's not a circle, right? Like we don't know whether it's a circle or not. It's actually not a circle.
Very close to, it's more.
Yeah, for Earth, it will be very close to.
M2G is equal to G M1 into R square.
M2G, what is G?
It's gravitational constant.
M2G? What is G? No? What's Newton's law? I mean, okay, I think you guys know all this, I think maybe you're not seeing what I'm asking. Okay, Newton's law says that mass times acceleration, we are talking about M2, times the acceleration of M2, right? It's a vector, is equal to the force acting between them. There's only one force, the gravitational force. It is G, M1, M2 over R, which is this distance. So it should be R1 minus R2 square. And this is a vector equation, so it's minus R hat. Right, that's all. So that's mass times acceleration is equal to force, right? And it's a vector equation. Okay. Let me clean this up and let's let so this is usually not the case. Let M1 be very much larger than M2 and let M1 be at the center, at origin. This is just for simplification, and later on, when we really do the couple of problems, we will actually not assume all these things. We will actually keep M1 and M2. In that case, R1 minus R2 is R squared, right? And A2 cancels out, but let's keep that. So M2 A is derivative of, I can write this as d by dt of M2 times velocity. There's only one velocity you're talking about, and that's equal to minus G M1 M2 over R squared times R hat. Okay, so that's our equation again. We like to write it like this because we want to see the Lagrangian. So again, we say, what's the Lagrangian? We know that the derivative of the Lagrangian with respect to velocity, this time a vector, vector will be equal to M2 times V. And the gradient of the Lagrangian with position is equal to minus G M1 M2 over R squared times R hat. Correct. This immediately tells us again that L is half M2 V squared, which is V dotted with V, and probably there are other terms which are position dependent. What does this tell us? Maybe think of this, if this helps. This is, remember, gradient, right?
Gradient doesn't, it should be
Gradient of what is having this structure?
gravitational potential.
Good. That's a good insight to have. Yeah. So you don't really have to do the math. You can, but still tell me what is, yeah, you can use in intuition or the physical intuition that you already have, because this should be related to the potential. What is this equal to? A gradient of what is, think of vector equations. Or maybe the question,
Gradient of in the X, Y, and Z.
gradient of what is, let's say, R hat over R squared.
That's the right.
1 over R cube, let's try it. So gradient of 1 over R cube, that will be equal to minus 3 over R raised to 4, and then gradient of R. How much is gradient of R?
1.
No, R hat.
So R value.
Right, so this is equal to minus 3 over R raised to 4. R hat, that's not what you want. So what should you have here, which will give me this? One over R, right? Very good, so it is minus one over R and this, so this is one over R, right? So that tells us that the minus goes away, so minus one over R, right? So probably L seems to be minus of, we want the G M1 M2 as it is there over R, right? Which is the gravitational potential energy, right? That was the intuition you were suggesting. And again, this can have velocity dependent terms. So what is the Lagrangian? Expectation of the Lagrangian is kinetic energy minus the potential energy. Oh, is this correct?
Yeah.
Did I do this
Minus.
correct? Oh, this is plus, right? This is not, like from here to here, when I wrote this, this is not minus,
yeah,
right?
yeah,
So this
minus.
is, yes, so gradient of something is negative, so this should be plus, correct?
Yes.
That's not the potential energy is a negative of that, but then Lagrangian is kinetic energy minus the potential. So it is plus GM1 into over R. Oh, this is M2, right? M2. Again, assuming that M1 is really large, right? Equations. Let's check. So we have the Lagrangian, check it out again. So that our action will be now a position, it's position dependent, right? No velocity dependence. It is that's your action. So that's your T1 to T2, dt, and half M2 dr by dt square and plus G M1 M2 over R. Notice when this R is not here, this is a vector R. Every time you see a magnitude of an R, you should think of this as square root of R dotted with R. Right, often this is a variation in a vector R you make. This is a scalar R, so you should be careful of how to relate. Okay. Or have the gradient always in mind. So we can try that here. So what is the variation of the action with respect to R as a function of, let's say, T prime? Okay, that's equal to T1, T2, dt. I have 2 goes away, so that's 2 times dr by dt dotted with d by dt of delta of t minus t prime, right? That's your first first term. And the second term is I have to make a variation in R due to a variation in the vector R. So this will be equal to minus of G M1 M2. First take the partial derivative of R, that's R square, and then make a variation, correct? So this will be equal to so I have to, yeah, so maybe I should be careful. So this is 1 over R, and I'm making a variation in R. This is equal to 1 over R dotted with R. And this will be minus 1 over r square. And then I have to do a gradient of r. And that gives me r hat. So this is minus 1 over r square times r hat. And then comes the variation in r itself. Or variation in r. So variation in r at t prime with t with a variation in r with t prime. Okay. Oops. So that is a r hat, r square, and so on. I think that's r hat. And that is a delta of t minus t prime. Okay. So that's your that's a generalization of into a vector. If you want. Make it clear how this is coming in, so make sure you understand that. Action principle says that you set this to 0. And the delta function can be evaluated, so you have d by dt of m2 times velocity is minus of r hat and g m1 m2 over r squared. And that's your equation you started with, but this time we got it by using Euler-Lagrange equations if you want. Next comes what's a Hamiltonian, right? If we have the Lagrangian, our goal is to find the Hamiltonian. So write the Lagrangian again of m2 v square minus of the potential, so it's plus, right? Plus g m1 m2 over r. What's the canonical momentum? So canonical momentum, let's write it again. Canonical momentum. In this case, again comes out to be simple. P is a vector. It's dl by dv. Is equal to m2 times v. Vector. So that's the only difference. Hamiltonian will be v dotted with p minus the Lagrangian. That's equal to there is a v dotted with p minus of half m2 v squared and minus of g m1 m2 over r. Let me do a quick convincing for you that this is really independent of velocity. So we have our Hamiltonian in this form written as v dotted with p minus half m2 v squared plus g m1 m2 over r, right? And remember that also
Minus zero.
oh minus because gravity is attractive. Thank you. Yes, okay, correct. Yeah, thank you. And p, the canonical momentum, is m2 times v. I have been trying to convince, emphasizing the fact that Hamiltonian is never velocity dependent. It is not there, but how do you check it? If there is no velocity, what will this be equal to? If I take the derivative with velocity? It should be 0. If there is no dependence in velocity, it should be 0. So let's do this. So this was a function written in form of velocity and p. So in this case, this comes out to be p. Right, if I take the derivative with respect to velocity, that's p, and here this will be minus m2 times v. And there is no velocity in here. But this is equal to the same using the definition of canonical momentum. So that's correct. So that's the reason why we should always take away the velocity dependence. So this suggests that we should not write our Hamiltonian in terms of velocity. Put this back in here. So this is P over M2. So that's P square over M2 minus of M2. Velocity is P square over M2 square and minus G M1 M2 over R. And that's P square. That's your Hamiltonian. Once you have the Hamiltonian, we should again try to get the Hamiltonian equation for motion. So it's a Hamiltonian. Of motion, which is the R by dt. This R by dt is equal to the partial derivative of the Hamiltonian with respect to momentum and total derivative of the momentum is negative partial derivative with respect to R. That's R. So let's see what it is. So partial derivative of Hamiltonian with respect to momentum is just the first term. So that's P over M2. And the partial derivative of the Hamiltonian with respect to position will be negative G M1 M2 and the gradient of 1 over R. We just did the gradient of 1 over R again to the partial derivative. So that's G M1 M2 and this is minus 1 over R square and then the gradient of R. Right, it's like a chain rule. And gradient of R is good to remember that this is R hat. A very useful identity in electrodynamics or any vector calculus. It's sort of a axis independent or basis independent representation. So that's equal to G M1 M2 over R square times R hat. So our Hamiltonian equations of motion become dr by dt is equal P over M2 and momentum time derivative of the momentum is the force, right? Force is attractive, so it's P M1 M2 over R square. Same idea, if I put in P is equal to mass times velocity, it's exactly the same equation, so you don't have anything, nothing changes as far as the motion of planets is not at all going to change, but we have an understanding that this is a minimization of an action that is giving you this, and that's a universal principle. You see that there is a minimization of a quantity. Okay, helps. So it gives you an idea of how you go from Lagrangian to the Hamiltonian. Find the canonical momentum, write V dotted with P minus Lagrangian, and get rid of the velocities. And sometimes that getting rid of velocity is because it is cyclic. It seems like it is a little confusing, but always it will go away. It has to go away. Okay, so we did a vector problem and a one-dimensional problem. Let's go back to simpler problem. Simpler problem is reasonably involved, and we will do that in detail soon. But here, let's, in the few minutes we have, just as an illustrative example. Let's do any problem in Newtonian mechanics using Lagrangian. Like, think of a simple problem in Newtonian mechanics. Something that is simple enough and or let's be honest, what's a favorite problem in Newtonian mechanics? Don't have dissipation in it.
Inclined plane. Motion
Inclined plane, sure.
Or something driving with friction.
No, don't put dissipation.
Oh.
Lagrangian is not very friendly with dissipation. Right, so we need conservative forces, remember? When we said Lagrangian should be, or force should be the negative gradient of a potential energy. Or we need potential energy, right? We need problems which has potential energy in it. Inclined plane
On a
is
frictionless surface. Motion-
frictionless surface, and if you have an inclined plane, that is pretty reasonably good problem that you can analyze using Lagrangian. So let me try to let's try to do that. So mass moving on an inclined, relatively simple problem. We're going to write the Lagrangians for it. So that's angle theta. And one of the things always one realizes in the Lagrangian very quickly is that dynamics is happening along a parameter space. Here, everything is happening along this line. Right? So if you have a mass m, it is this line along which everything is happening. Even though you would say you would begin with x and y here, let's say this is x and y. Very quickly you learn that, it is these coordinates that is more interesting or more useful. Right, this could be x and y, this could be x prime and y prime, let us say. If this point was x and y, x prime, y prime, let's say. What is it in terms of x and y? Is that a better thing to say? Or let me say, let's say this is x and y, and let me call this distance x. Let me not say anything of this. No, this is x and y coordinates, and let me say this is s. And that could be your origin, right? That's your 0. Better? Right. And these are our distances. So that's your y and that's your x. So it is clear that s squared is equal to x squared plus y squared. Better? Think so? And yeah, maybe. Yeah. Okay. So we will begin with the Lagrangian. So Lagrangian, now that we have seen various situations, let's guess, right? Let's guess the Lagrangian to be kinetic energy minus the potential energy. What is the potential energy in this case?
mgy,
Mgy, the height, right? Mg, and it's only the height that matters, and we are saying that that is y equal to 0 somewhere. Right? Now there are two parameters here, x and y. So apparently Lagrangian is equal to half m, velocity is x dot square. So this is dx by dt square plus dy by dt square. Minus mg. It's 1. Right. And we also have this angle theta, which is fixed. Okay. What is x and y in terms of the variable s? We can immediately see that x is equal to s times cosine theta, where theta is fixed, theta is not changing with time, right? And y is s times sine theta. Right, remember theta is fixed. That's the inclined angle, so it doesn't change with time at all. So what is dx by dt? This is equal to only ds changes with time, and cosine theta remains as it is. And dy by dt is equal to ds by dt times sine theta. That immediately tells us that dx by dt square plus dy by dt square is equal to square of this plus square of this cosine square plus sine square theta. So that's ds by dt square. That's primarily because of the constraints. You notice what is happening is that even though x and y are two independent variables, mostly it is only s that is changing. There is a constraint, there is a line along with everything is happening, so there is a constraint there. Lagrangian then is equal to half m ds by dt square and minus mg. What is y? Y can also be written in terms of s, which is s sine theta, right? So it is s sine theta. Where sine theta is fixed. And this quantity depends only on s. Right? It depends on s as a function of time. It, if you want, depends on the velocity, ds by dt and t. Once you have everything described in terms of one variable, or even if it is two variables, doesn't matter, then we have a Lagrangian, you can write an action, right? So the action, which now is dependent on s, will be, say, t1 to t2 dt of m s by dt square, and we have minus mg s sine theta. Make the variation in the action, and we should get our equations of motion. I think this is the first problem where we did not start from Newton's laws. We started from the Lagrangian directly, and we are getting the Newton's law. We could have written the equations first and then motivated our analysis.
Start with the action, get the.
Yes, so here we pretended that we don't know the equations of motion. We could have, right? This is an elementary problem. We could have written down Newton's law and got the equations and then tried to get the Lagrangian. Here, I directly assume that it is kinetic energy minus potential energy, right? So there's
There's something.
a strategy change that I made, or this time I really started with the Lagrangian. And then got rid of one of the variables, like there are two variables here, x and y, then I got rid of one of the variables, saying that there is a constraint. This is called a constraint, right? So this is. So you will see this again and again, that whenever we have a motion, some of the variables are constrained to be along a path, like sometimes it is on a circle, like when a pendulum is moving, it is on a circle, right? The mass is on a circle with equally distant from the point. In this case, it is on a line. So always there is a constraint, and that allows us to get rid of some of the variables. We'll see that happening again and again. So action, that means we can now change the action. So there's this creation of S as a function of E prime. So this switches on the other side, so this is minus d by dt of m ds by dt. That's your velocity. This is minus, right, minus mg s. And it is coming up with the opposite sign because our s is different like this. Right? So this tells us that this is acceleration, right? Mass times acceleration is equal to minus mg s sine theta.
S will be
What is wrong? Oh, S is not, yeah, thank you. And did I get the sign correct?
Yeah.
Thank you. Is this what you get? Is this correct equation? Is this correct equation? So maybe.
Yeah.
Let me argue it is, so let me confuse you guys, this is elementary, right? So I should be able to. So this is your mass, right? That's your mg. There's a normal force. Right? And you would say mass times acceleration, that's Newton's law, is equal to mg, that's a force, not a vector, like the vector has the directions in it. And now let's split this into this axis. So that's your x and that's your y. In the x direction, I have mass times acceleration, positive, right? Mass times the acceleration. And mg has a component, so it is in the fourth quadrant, so mg is positive, so it is mg sine theta. And normal force doesn't have a component, right? So acceleration is, or ma is equal to mg sine theta. Okay. Positive. So what happened here? And that is a normal force also there, that, so in the y direction, you have no acceleration. It is minus mg cosine theta plus the normal force, which is normal force is equal to mg cosine theta. This is the constraint equation. We won't see that in the Lagrangian. Later on, again, we will come and try to capture that using Lagrange multipliers. But the question is, what went wrong? Or did something go wrong at all? Why are we not matching with the sign?
if we take action principle, it will be positive again.
We did take the action principle, right? I'm setting this to 0, right? To get this,
Yeah,
right? I set this to 0.
yeah, one will be positive.
So this I moved it like, yeah, so this became positive.
That one is, okay.
Correct?
Yeah, it's okay.
So why is it not matching with this? Could we have done something wrong?
you know, you have a, is it good to, you state the direction, should be positive in one diagram and
That's very
the
good.
direction is split on,
Yeah, we set our origin here.
Yeah.
So S is positive to the left. Right? So S is increasing in this direction.
Yeah.
Right? That's my S. But X is, this is written in terms of X, right? So this equation is basically mass. Second derivative of S over dt square is equal to minus mg sin theta. Right, when I say acceleration is second derivative of S, here when I say acceleration, it is md square x over dt square is equal to mg sin theta. Right? And x here is along, by the way, x, I should be careful, this is not the same x here, right? So, but I think I wrote that like that. So here x is increasing to the right, and here s is increasing to the left. And so this is correct. There's nothing wrong in it, it's just that our variables are adding unusual, like we are used to writing acceleration in the direction it is moving, but we don't have to. We can always use a variable in the opposite direction, and that's why that negative sign shows up. That's clear, shouldn't be confusing.
yeah. Usually remember it's a minus, it's usually direction.
Yeah.
It's-
Okay, so we can do some of these kind of examples in example, right? So I'm going to Lagrange and something like that. That's all, okay.